In this video, I'll talk about the way numbers are represented in computers and how this affects the accuracy of calculations. The point here is not to provide an exhaustive discussion of this topic, but to make you aware of some of the pitfalls of numerical computing so that you can recognize them when they occur. The first thing I need to talk about concerns numbering systems and how computers represent numbers. Humans use a base 10 numbering system, which is just because we have 10 fingers. A base 2 numbering system is typical for computers, since computers have only two states, on and off, or equivalently high and low voltage. Now I'll introduce some terminology relative to numbering systems. Both binary and base 10 systems are positional numbering systems. That just means that the position of each digit in the number provides information about the number. More specifically, the position provides a weight that represents the power of what's called the radix. The radix of a numbering system is the same as the base. So the base 10 numbering system's radix is 10. Radix 10 numbers are interpreted as in this example. The number 847 is interpreted as 7 times 10 to the 0th, since the last position in the number is the 0th position, plus 4 times 10 to the 1st, plus 8 times 10 squared. Binary numbers are interpreted in the same way, but they have only two digits, 0 and 1. Each digit, by the way, is called a bit, which is just short for binary digit. As an example, the number 1011 in base 2, this subscript here is used to denote the radix of a number if there's any possibility of confusion, is 1 times 2 to the 0th, plus 1 times 2 to the 1st, which is this position, plus 0 times 2 squared, plus 1 times 2 cubed. In base 10, this is 8 plus 0 plus 2 plus 1, or 11. Computers mostly represent numbers in two different types, integers and floating point numbers. Integers have no fractional part, which makes them easier to use when illustrating how numbers are represented in computers. Integers are represented in computers by a specified number of bits. So I can specify an 8-bit integer, a 16-bit integer, and so on. The more bits in the number, the larger the range of numbers that can be specified. I can also specify an integer as being either signed or unsigned. Signed integers can be either positive or negative, while unsigned integers are always positive. To represent a signed integer, one bit is used to denote the sign, positive or negative, and the other 7 bits represent the number itself. For example, an 8-bit unsigned integer can be used to represent numbers from 0 to 255 in a base 10 numbering system. Notice that we have 256, or 2 to the 8th possible combinations here. An 8-bit signed integer can represent numbers from negative 128 to positive 127. This is still 256, or 2 to the 8th possible combinations. A 16-bit integer has 2 to the 16th possible combinations, which can represent base 10 numbers from 0 to 65,535. Now let's talk about how integers are specified and used in MATLAB. MATLAB allows you to create both signed and unsigned integers with 8, 16, 32, or 64 bits. The command to create a signed integer is int followed by the number of bits. Unsigned integers are created by a command starting with uint and then the number of bits. So int 8 of negative 13.5 converts the number negative 13.5 to a signed integer. The result will be negative 13. If I converted negative 13.5 to an unsigned integer, the result would be positive 13. uint 16 of pi converts pi to 3. It's an unsigned 16-bit integer. The type of data associated with a variable can be displayed with MATLAB's class command. One thing to keep in mind is that MATLAB won't do arithmetic with variables that have different data types. So you can't, for example, add an 8-bit signed integer to a 16-bit unsigned integer. Now I'll do a couple of quick demos in MATLAB. Let's create some integers and see what happens. First, I'll convert pi to an unsigned 8-bit integer by typing uint 8 of pi. The result is 3. MATLAB throws away the fractional part of the number. Now I'll create a variable x, which is an unsigned 8-bit integer version of negative 17,256. Since unsigned integers can't be used to represent negative values, the result is 0. Now I'll create a variable y by typing int 8 of 75,563. The largest signed 8-bit integer is 127, so anything above that value is thrown away. The extra bits needed to represent the larger number overflow out of the 8 bits available to represent the number, so the difference between the actual number and its 8-bit representation is called overflow error. To see the data type of the variable y, I can use the class command. It's displayed as being a signed 8-bit integer. The who's command also displays the data types of the variables in the workspace. The other main data type used in MATLAB to represent numbers is floating point. Floating point numbers have non-zero fractional parts, like pi or 14.75. They're always represented in terms of exponential notation, which has a mantissa. In this example, that's 123.45, and an exponent, 67 in this example. In MATLAB, the mantissa must be represented by a number that is between 0 and 1, with the first digit to the right of the decimal place not being a 0. For example, the number 36.3 would be represented as 0.363 times 10 squared. This is important because of the way MATLAB interprets the bits in a floating point number, which in turn affects the range of possible values that get used in our calculations. If you don't assign a different data type to a number in MATLAB, it will create what's called a double precision number, which uses 64 bits to represent it. Of the 64 bits in a double precision number, 1 bit is used to specify the sign. The number can be either positive or negative. 52 bits are used to represent the mantissa, and 11 bits are used to represent the exponent. With this allocation, the largest number we can represent is about 10 to the 308th, and the smallest number is about 10 to the negative 308th. The exact values are available as predefined variables in MATLAB. The largest value is called real max, and the smallest is real min. Now, here's the important result of all these factoids. Arithmetic in computers has what's called finite precision, which we probably all knew within the first minute of the previous video. However, now we can quantify exactly what this means. So if you've dozed off during the previous slides, please pause the video, stretch, and splash some water on your face so that you're awake for this slide. When doing math with floating point numbers in computers, the accuracy of the result depends on the mantissa of the number rather than the exponent. This means that the accuracy is limited by the least significant bit of the 52 bits used to represent the mantissa. The number corresponding to this bit is designated by epsilon. The result is this rather strange mathematical expression. This has no meaning in terms of symbolic mathematics unless delta is exactly 0, but it's super important in numerical mathematics. If I add a number delta, which is less than epsilon to 1, the result is exactly 1. The implication of this is that if I try to do arithmetic with numbers that are as small or smaller than epsilon, I can't depend on the results. They'll likely be garbage. If you want to see what the value of epsilon is in MATLAB, it's provided in the variable named EPS. The number's about 2 times 10 to the negative 16th. Now I'll go to MATLAB and do some demonstrations relative to these concepts. First, I'll display the largest floating point value we can represent by typing real max and pressing enter. The smallest floating point value is displayed by typing real min and pressing enter. MATLAB thinks that numbers whose absolute values are above and below these values don't really exist. For example, if I try to multiply real max times 10, MATLAB displays the result as infinity, or INF. What MATLAB is really saying here is that the number I'm trying to calculate is bigger than the largest number MATLAB knows. Real max and real min are all about representing numbers. Next, let's talk about the accuracy to which we can do arithmetic. Arithmetic is governed by the least significant bit of the mantissa of the numbers involved, which is the number EPS in MATLAB's workspace. EPS is about 2.2 times 10 to the minus 16th. If I try to subtract a number that's less than EPS from 1, MATLAB thinks that the number is exactly 1. So 1 minus EPS over 5 is exactly the same as 1. As you may guess, one problem associated with finite precision arithmetic is its use in logical operations and decision making. As an example, the tangent of a number is just the ratio of the sine to the cosine of that number. So if I calculate a variable, x equals tan of pi over 6, this should be equal to the sine of pi over 6 divided by the cosine of pi over 6. So I'll create a variable y that's the ratio of the two. If I take the difference between these, I should get 0. So x minus y is not 0. It probably comes as no real surprise now that the result isn't exactly 0. However, one might think that a number that's on the order of 10 to the minus 16th is close enough to 0 to make no difference. Most of the time, that would probably be correct. But relational and logical operations, for example, don't really leave any room for error. Let's use these values to make a decision in an if construction. So, if x is equal to y, I'll display x equals y. If it's not, I'll display x not equal to y. And end. MATLAB recognizes the two numbers as not being exactly equal. In general, checking for equality between two floating point numbers, particularly numbers that are the result of a calculation, is a bad thing to do. You should always take into account finite precision effects when doing logical statements, and especially try to avoid checking for strict equalities whenever possible. This concludes my discussion of the problems associated with numerical analysis compared to the symbolic calculations we've done in math classes. The main point here is that you should be suspicious of any result that you get from a computer. Always cross-check your results to make sure they make sense. Errors can creep into calculations in a variety of ways. You might have made an error in your calculation or program which you can find and fix. Or you can possibly just be expecting too much from the computer, and unavoidable errors like round-off and finite precision effects are making your results unreliable. Now we can finally stop talking about programming structures, syntax, and how computers work, and start doing some numerical analysis to solve realistic engineering problems. We will still use all the tools from the previous parts of the course, but the context will be different since the focus will be more engineering related.